I'm going to present our research on a hardware unit that enables modular and scalable support for atomic operations in a shared memory multiprocessor. This is a collaboration between the IAS and the SPCL at ETH Zurich and the University of Bologna. So, as you probably all know better than I do, parallel algorithms require non-blocking synchronization to scale. Essentially, due to Amdahl's law, even if only a small part of an algorithm requires serialized work, the performance of that algorithm does not scale with an increasing number of threads. And blocking synchronization means serialized work. Now, atomic memory operations, or AMOs for short, are central for non-blocking synchronization. One well-known example of an AMO is fetch and add, where each thread obtains a unique ID from a shared counter, for example. The usage of AMOs also enables progress guarantees in concurrent algorithms. Lock freedom means no locking of shared resources, which allows at least one thread to make progress. Wait freedom is an even stronger progress guarantee and means that the execution time of each thread is bound. Due to their importance, AMOs are implemented by many processor architectures today. However, implementing them in a scalable way is not trivial. Because implementations are commercial secrets, there is a knowledge gap on this topic. From experiments and the few open source implementations, however, we can infer that AMOs are mostly implemented as tightly coupled to the processor architecture or the memory hierarchy. For instance, in the figure on the right-hand side, you see an experiment on an Intel processor. On the x-axis, you see an increasing number of concurrent threads, and on the y-axis, you see the bandwidth the algorithm achieves. Now, an algorithm with only writes, which is the topmost curve here, to the same memory location scales relatively well. However, when those writes are replaced by atomic memory operations, such as compare and swap, CES, or FAA, fetch and add, which is the other curve, the bandwidth actually decreases with an increasing number of processors. This can be observed also on other processors. So this is an Intel server architecture. So we can conclude that current implementations of AMOs scale poorly to a large number of threads. And this is presumably due to either cache line locking or cache line bouncing. Now in this work, we design, implement, and evaluate a hardware unit called atomic unit, or ATUN for short. To overcome the limitations of other AMO implementations, it is a modular design, meaning that it is independent of the processor and the memory controller and can be inserted at any stage of the memory hierarchy. It executes AMOs without locking a shared resource or bouncing data back and forth between different memories. And because this implementation is open source, we are able to close the knowledge gap. For tangibility, we target RISC-V, which is an open instruction set architecture, or ISA for short. It's organized in modular extensions, and the standard A extension specifies two kinds of atomic operations: load reserved, or LR for short, and store conditional SC, as well as AMO's atomic memory operations. Now, load reserved and store conditional open a window with a load, you get data, you place a reservation on the memory, and then you can execute essentially any operation within a short window of instructions, which you conclude by a store conditional. The store conditional only succeeds if the reservation is still held by the same thread that placed the reservation. If the store conditional does not succeed, it fails, the processor is notified of the failure, and it has to retry its operation again. This is the benefit that you can implement essentially any atomic read-modify write operation, but because it can fail, you sometimes waste work. In contrast, AMOs specify only a very specific set of read-modify write operations, which covers the set of STD atomic operations from C++. So these are AMO swap, add, and etc. And by definition, they must not fail. So an AMO executed never means wasted work. One terminology from RISC-V is that a hardware thread is just abbreviated as a heart. And second, we also need an on-chip communication protocol to which we need to stick to. Now, we target AXI, which is a state-of-the-art and industry-dominant protocol with an open specification. It enables high-performance communication by allowing bursts, multiple outstanding transactions, and transaction reordering. It specifies exclusive operations, which we can use to implement LR and SC, and AMOs, which are a superset of those in RISC-V. We will not dive very deeply into the technicalities of AXI here, but a short overview is helpful. So AXI is a point-to-point protocol, meaning one master talks to one slave. This is AXI standard terminology to which I adhere for the sake of clarity. Reads and writes take place on independent channels. There are 3 channels for writes, namely write command, write data, and write response. And there are 2 channels for reads, namely read command and read response plus data. Here you can see an example of a subset of the channel signals. So this would be a request for a write to some address C, an atomic operation that is performed, which is an add, and then some data to be added to the current value at that memory. At some point later, the slave responds with a write response and also with a read response, because the write response does not contain data. It just says that the write has concluded, whereas the read response contains the actual data before the AMO was executed. Our atomic unit has 2 standard AXI interfaces, a slave port and a master port. It is independent of processor cores and memory controllers and can be placed anywhere in the memory hierarchy. Upstream masters, here on the left, send atomic transactions, and the ATUN translates them into regular reads and writes. This means that downstream slaves, such as memory controllers, do not have to deal with atomic transactions at all. The atomic memory unit is composed of 2 stages. The first stage, and each stage has its distinct purpose. The first stage is the AMO stage. It contains an ALU to compute atomic operations, and it emits exclusive loads and stores, or LR and SCs, to the LRSC stage, and relies on the LRSC stage for atomicity guarantees. And the LRSC stage handles the memory reservations and deals with memory consistency. It only implements LRSC, no AMOs, but that is sufficient to guarantee atomicity. So let's go a bit more in detail of the 2 stages. First, the LRSC stage. This stage has a reservation table as its central piece. This table stores 1 reservation per hardware thread, per heart, and it is set by a load reserved. Any write will clear all reservations for the same address, and the store conditional then only succeed if the heart with that ID that sends the store conditional has a valid reservation at this point. So let's look at a short example. Assume that initially we have a reservation from heart 0 at address 4 and 1 from heart 2 at address 8. Now, core 1 or heart 1 issues an additional load reserved to address 4, and the LRC stage stores this address in the reservation table. After some time, without any writes to the same address, to address 4 in between, the heart 1 completes its atomic read-modify write with a store conditional to address 4. This now means that this write by heart 1 goes through to the memory, since its reservation was valid, and that all reservations to address 4 are cleared. Now a bit later, Hard 1, which initially also had a reservation on address 4, also issues a store conditional. But that one fails because its reservation has been cleared by now. And this write transaction does not go through, and the core is notified of the failure. The AMO stage executes one AMO at a time and does not block other AMO transactions while executing one. So let's go through an example also here. Assume that a hard sends an AMO transactions on one of the write channels. This then triggers a read to downstream memory, since the ALU first needs to have the second input value here. So one input value comes from the hard that sends the atomic, for example, increment, and the other one has to be read from memory. So the AMO stage sends a read transaction downstream. It then gets a read response with the data, which forms the second input, and those are computed together to form the new value, the updated value of the memory location. And the result is then written back to the memory slave via the write channels. And as soon as the write response from the slave arrives, the AMO stage sends a write and a read response back to the master, meaning that the memory location has been updated with the write response and the data prior to the operation with the read response. So given this implementation, we wanted to know whether it can really scale up to the limits of a memory controller. We therefore evaluated the throughput on a system with 32 RISC-V cores on an FPGA. The 32 RISC-V cores are organized in 4 clusters of 8 cores each, and we place our atomic unit in front of the shared L2 scratchpad memory. We measure the bus and memory utilization before and after the atomic memory unit with AXI monitors, and we measure the throughput with hardware counters in the cores. And second, we are also interested, since we designed hardware, in the actual silicon complexity. So we evaluated it in a modern silicon technology up to 128 cores. To tie back to our introductory example with the Intel processor, we are first interested how the ATUN performs under worst case conditions. So on the x-axis, you again see an increasing number of cores, and on the y-axis, you see the throughput of the system at 1 gigahertz. With only writes, the blue curve here, we find the roofline of the platform. Because the memory controller, which also runs at 1 gigahertz, can handle 1 read or 1 write every second cycle, it saturates at 500 megaops per second. So this is the roofline of this system. Now, load reserved and store conditional pairs achieve half of that because they consist of 2 transactions, 1 load and 1 store. This means that they fully utilize the bandwidth of the memory controller, and the ATUN is not a bottleneck for them. AMOs achieve a throughput of up to 100 megaops per second. This is because each AMO takes 10 cycles due to the injection of a read, which takes 2 cycles, the calculation, which takes another couple cycles, and the write, which takes another 2 cycles. So while load reserved and store conditional scale perfectly, the AMOs take 10 cycles, which could be improved by a more advanced architecture of the AMO stage. Nonetheless, we note that this scaling is much better than what we currently see on commercial server processor. Now, this is a synthetic and worst case scenario. What about real algorithms? We first evaluated a state-of-the-art concurrent queue algorithm. This algorithm has only 2 atomic variables, one for the read pointer and one for the write pointer. This means, like in the previous benchmark, contention will still be very high, actually almost as bad. But still, it's a real-world algorithm, so there is not only atomic operations performed, but also some work performed between pointers are updated. We implemented the algorithm once with AMOs, which is the orange curve, and once with LRSC, which is the green curve. As you can see, the AMO variant scales slightly better, Because store conditional, so the LRSC curves here, they will fail relatively often due to the high contention. Now, when we look at the memory utilization, we can see that both versions fully saturate the memory bandwidth. We conclude that both LRSC scale well in a real-world situation up to the limits of the memory controller. For the second algorithm, we implemented a log-free memory allocator. We also implemented two versions, one with only AMOs, which is the purple curve or light red, and one with AMOs and LRSCs, which is an optimization of the original algorithm in blue. As you can see, the version with only the AMOs cannot fully saturate the memory controller. And this is due to the limitation we've seen earlier in the synthetic worst case scenario, where the AMO stage can only execute a new AMO every 10th cycle. So our optimization, which replaces some of the AMOs with load reserved and store conditional, resolves this bottleneck and again achieves almost perfect saturation of the memory controller. Finally, we looked at the hardware complexity in a 22 nanometer FDSOI technology from Global Foundries. We synthesized the entire system that we discussed in the beginning at 1 gigahertz. And the ATUN is not on the critical path, meaning it does not limit the 1 gigahertz. It could go even faster, probably up to 2 gigahertz at 22 FDSOI. As you can see on the right-hand side, we have an increasing number of hearts cores up to 128. And on the y-axis, we have the area in a technology-neutral unit. The reservation stage, which contains one reservation slot per heart, grows linearly with the number of hearts. And all other components grow either logarithmically or not at all. So we have one component that grows linearly, but all other components are essentially independent in terms of complexity from the number of hearts. So in conclusion, we have presented our atomic unit, which is a modular implementation of atomic memory operations that is independent of the processor and memory controllers. It does not lock shared resources, and it scales onto the saturation of the memory controller in every but the most extreme cases for AMOs. We have evaluated it in real hardware, both cycle accurately on an FPGA for throughput, but also in a modern silicon technology for hardware complexity. Our implementation is open source. You can download the full source code and improve it if you want on GitHub. So we fill and contribute to we fill the knowledge gap and contribute to further development on AMOs.